Okay, so let's see. I want to start off just by taking a look again at what we did yesterday, trying to summarize that before we go on today. So what we said yesterday was we've got the standard model of particle physics, which is remarkably successful. Perhaps one of the simplest predictions we may want to verify is, well, the standard model predicts there's such a thing as an electron. What would we tell an experimentalist to measure if we wanted this experimentalist to measure an electron? And we said that a good thing to ask an experimentalist to measure would be the energy of the electron and momentum of the electron, because knowing these quantities, we could calculate the mass. We then said, but hang on, what momentum should the electron have? In which direction should it be going, and what should the magnitude of that momentum be? And we concluded that, in fact, it does not matter. The electron can be moving in any direction. It can have any magnitude, and the mass that we measure will always be the same. So this was a good label for the electron. And we wanted to get some insight into whether there were other good labels and why this was a good label. So the way that we said that we would tackle this problem is we would have some sort of an operator which would implement a transformation on our electron. So it could do something like change the direction of the momentum of the electron, or perhaps if the electron was at rest, give it some non-zero velocity. And our question then became, which labels for the electron would be invariant under that set of transformations? To start making progress with that question, we extracted a couple of properties that we said were true for any set of transformations. And this led us to the definition of a group. We then said, well, this is true for any set of transformations we may want to consider. So let's write down something that's more specific that would be consistent with only one group. And what we did to do that was the multiplication table. So we refined our closure axiom. We said, if we take this element and compose them, we will get that element. And that was a characterization, complete characterization of the group. We then saw that we were able to realize that multiplication table in terms of a number of different sets of objects with a number of different rules for how we compose the group elements. And another thing that is clear is that by using one of these concrete representations of the multiplication table, we may be able to derive certain equations which don't follow as a consequence of the multiplication table, but they also use some properties of the explicit realization that you are looking at. Because of that, we wanted to make a distinction between a representation of the group and the abstract group itself. We then asked ourselves, well, how many representations are there? We quickly learned that if we had even a single representation, we could find an infinite number of other representations which were equivalent to the representation that we had. If we had even a single representation, we could build up an infinite number of representations from this one by just taking some sort of a block diagonal form. So we said we had a whole lot of representations that were that could be built just by repeating our basic representation. And we called representations of that form reducible. Yesterday, we stated our intention that we were going to focus on equivalent reducible representations. One question that I was asked a couple of times yesterday, so let me give the answer to that, I didn't say this explicitly, was the following. If I have a matrix acting on a vector, which gives me, let's give this a label I, vector I. When I want to calculate the trace of this matrix, I can calculate the trace of that matrix in any basis that I want to. Okay, the result of calculating the trace is basis independent. You can check that for yourself because of cyclicity of the trace. So what we learn is the trace of matrix M is a sum from I is equal to 1 to D of lambda I. So when I was equating traces, some of you weren't sure how was I turning that into a statement between eigenvalues. Well, just go to the basis in which M is diagonal, and you'll see why tracing M was a statement about eigenvalues. Okay, so let's proceed now. So this is great. we claim that we have a way to characterize a group by giving its multiplication table. So perhaps we should stop now and ask ourselves, well, how good is this characterization? Well, it turns out that this characterization is awful. It's not useful for most of the cases that we're interested in. You see, you might be interested in something like a translation. Now, if I want to specify a translation, I have to specify the displacement through which I will translate. There are an infinite number of different displacements through which I could translate. So even if I just wanted to write down all of the group elements, I would never finish writing them all down. So forget about constructing a multiplication table. That I won't be able to do, because I couldn't even list all of the elements. Same thing with rotations. I have to specify an axis about which I rotate. Well, that's got 2 angles in it. And I have to specify an angle through which I will rotate about that axis. Once again, that means that I'll have an infinite number of group elements. I can't list them all, so I can't stick them all in some table and tell you what they multiply to give. However, both rotations and translations are examples of what we call continuous groups. Now, when we have a continuous group, we can change the group elements smoothly. So we could say start from the identity and smoothly build up a bigger transformation. And that's what we're trying to do. So I've got a little demonstration of this. So what we're going to do, we're going to start off with a discrete transformation, and we're going to try to build up something that is continuous. Okay. So the case that I would actually like to start off with is a translation. So let's consider a function f of x. Under an infinitesimal translation, what will f of x do? F of x will go into the f of x plus epsilon. Well, you know what? Maybe if I perform an infinite number of these infinitesimal translations, maybe I can build up a finite translation. So maybe the only thing that I need to understand is infinitesimal translations. I'm now going to try to argue that what I've just said is correct. So how can I write the f of x plus epsilon? Well, if epsilon is small enough, I can write this as 1 plus epsilon d by dx acting on f of x. Okay. So what I would now like to do, I would like to say, well, let's try to build a finite translation. I am going to perform n translations. Each translation translates by some a divided by n, so that when I've done n of them, I will have translated through some finite displacement a, and I'm going to take n to infinity. So I'm taking n to infinity, and a is fixed, which is the displacement through which I want to move. So what do I have to study? Well, this is the thing I want to study. I've got 1 plus a divided by n d by dx raised to the power of n acting on f of x. And I want to take a look at this operator when n is very, very large. Okay? So let's try to figure out what that will be. Okay. So we've got u is equal to 1 plus a over n d by dx to the power of n. And I'm going to take the log of both sides. It's easier to study the log. Now, what do I mean when I take a look at this expression? How can I take the log of d by dx? I mean, this is an operator after all. Well, this side would be defined by power expanding the log. And then you would get d by dx acting on whatever you wanted. Well, if n is very large, this over here is going to be small. So I can write I've got n, and the log of 1 plus x when x is very small is just x. And when I write this down, I am neglecting terms of order 1 over n squared. When I multiply my n through, I just get a d by dx plus order 1 over n. Okay? That's log u. So what will u be? Well, u would just be equal to e to the a d by dx. Okay, so this would become e to the a d by dx acting on f of x. And we can now expand out that exponential. So I'm sure everybody knows the expansion of an exponential. Acting on f of x. Does anybody recognize this expression to be anything? What is this? This is the infinite order Taylor approximation to the f of x plus a. Okay, is everyone happy with that? So what we've been able to do is we really have been able to build up a finite translation by composing an infinite number of these infinitesimal ones. Now, when we write this e to the a d by dx, so this is now my translation operator, t of a is equal to e to the a d by dx, the way that I usually write it is I include some i's. I write this as e to the I a p, where p is equal to minus I d by dx. Now, why would I want to do that? Why do I include the extra i's in the definition? Well, there's a good reason for doing this. If I have an expression of e to the I alpha times by some operator O, okay, so this is some transformation that I could be considering. Okay, if I'm working in quantum mechanics, what would I like to have of that operator? Well, if I've got some sort of a transformation that would say boost an electron or rotate an electron or something like that, I would still like that the electron's wave function is normalized to 1. It's just now a boosted electron or a rotated electron, but I still have an electron. So what I would like from my transformation, I would like it if it doesn't change the normalization of my state. So it leaves my inner product invariant. Operators that leave your inner product invariant are unitary. So in quantum mechanics, the types of operators that we want to focus on are unitary operators. Let's write down the condition for this thing to be unitary. If this is unitary, what must we have? We must have the Hermitian conjugate of this thing. Must be equal to the inverse of this thing. Well, if we take the dagger, that changes the I into a minus I. So we get an e to the minus I alpha, and O becomes O dagger. Must be equal to, on the other side of the equation, to get the inverse, I just change the sign in the exponential, O. So what I learn is, for these two to be equal, I learn that O dagger must be equal to O. That's a Hermitian operator. In general, then, the operator that you stick here that is going to give you the finite transformation will be a Hermitian operator. And in general, Hermitian operators are observable. That's why it was no big surprise here that when we were looking at translations, we got hold of the